Okay, so now we are starting with a new topic today, and this topic is now there are two classes of logical circuits. One is the combinational circuit, and another is sequential circuit. In combinational circuit, the output is a function of inputs only. Like for instance, if we have an output C, so let's assume it's a combinational circuit. So in this case, let's assume we have this combinational circuit, and now this is the AND gate is a combinational circuit. So let's assume the A and B, and the output is C. So in the combinational circuit, the output is a function of the inputs only. Now, what about the sequential elements? The output is not only the function of the input; it also depends on the previous state. So can you see there is a feedback in sequential circuit? We will cover these sequential circuit later on in our later on. So now, if we are giving a combinational circuit, so can you see here there is a combinational circuit? Can you analyze its function? So whenever a combinational circuit is given, so the logical diagram is here is given. Can you analyze this function? Okay, and you please, everyone, please speak at least something. If you look at this circuit, how many inputs are this circuit? How many inputs are there to this circuit, and how many outputs are there? Can you tell me? Please, quick.
Two input, two output.
Very good. So now if you look at this circuit, so we first label the inputs, and please look at here, the inputs are in green color and the outputs are in blue color. So in this, let's say, oh, we have two inputs. What are the name of those inputs? We can give any arbitrary name. We can give A, we can say, okay, R stand for Rex, or Z stand for Zafar. So it can be any input and can be any output, like Mubin, the first output bobine, which is M. You can give any name to it. So we label the inputs and outputs. So now we are labeling the inputs. There are two inputs, we call this as A and B, and now there are two outputs, we call them as F1 and F2. You can give them any labels. Then obtain the function of the intermediate points. Okay, now if you look at the intermediate point, these are the intermediate points which are shown in the red color. So if you go to the intermediate point, so this intermediate point, what is this intermediate point? This is actually A plus B, and this intermediate point is actually A bar plus B bar. Okay, now we find the expression for the intermediate points, and now what is f1? Now f1 is a plus b dot a bar plus b bar. So this is now we have derived the expression for f1 and f2. Now if you look at f2, so please look at here, what is this f2? Now if you look at this f2, so this is actually a bar plus b bar. So this is a bar plus b bar, and we invert it. So this is a bar plus b bar, and then we invert it. Then we apply the De Morgan's theorem. When we apply the De Morgan's theorem, so we get this output. So this is actually when you apply De Morgan's theorem, we got a dot. Any question? Any question? Okay. So now when we do that, okay, so now we derive the truth table for this, and if you derive the truth table, we derive the truth table from this function. So now what is f1 is equal to a plus b. So now a plus b, so can you see here, this is a plus b. Now please look at here, this a plus b, this is a plus b, it's 0. So the output will be 0 when both inputs are 0, and the output will be 1. So the output will be 1 if any input is on. So we derive the expression for a plus b. Similarly, we derive the expression for a bar plus b bar. So this is a bar plus b bar. Can you see here this a bar plus b bar? So now this is, we derive the equation for a bar plus b bar, and then we derive f1. What is f1? F1 is a plus b dot a bar plus b bar. So what is f1? So please look at here. So this is my f1. So which is now the purple color. So f1 is a plus b, and a plus b is column 1, and a bar plus b bar, which is actually column 2. Okay, so what is f1? F1 is equal to c1 dot c2. So if we do 0.1 is 0, 1.1 is 1, 1.1 is 1, and 1.0 is 0. So now we derive the expression for f1 and f2. Similarly, we derive the expression for f2. And what is f2? Please look at here. What is f2? F2 is ab. And what is ab? The f2 will be 1. So in this case, f2 will be 1. F2 will be 1. So now this is f2 will be 1 if both inputs are ab or 1 1. Can you see here? So what we do, so what is the first step? We identify the label the inputs and the outputs, then we derive the expression for the intermediate points and the outputs, and then we draw the truth table, we derive the truth table, and then we deduce the functionality of the circuit. So now if you look at the functionality of the circuit, the first the first output is your sum, and the second output is your C out. And how? I will explain this. So now what I'm going to do, I'm now going to explain this. So can you see here now? This is actually, can you see here? This is my what I'm going to do. So what I'm going to do. So now this was my thing. Please remember what was this thingy. So what was the first input here? A and B. So now can you see here? This was the input A and B. So this was okay. Now what I'm going to do? So this was my input A and B. So I'm going to copy this thingy. Yeah, I'm going to copy this, Control C, and then I'm going to paint. Okay. Now, please look at here. So now if you look at this circuit at the block level. So these are my inputs. So A and B are my inputs. So A and B are now my inputs. So what are my inputs? So my inputs are A and B, which is the green color. And what is my output in this case? Can you all tell me? Please help me. What is my output? The blue color. Yes. At least speak. Please at least
F2.
F1 and F2. Okay, now when we say F1 and F2, so please look at here. So what is this F1 and F2? Okay, so let's assume if you are adding two numbers. Let's assume we are adding two numbers. So for the first combination, okay, now what is the first combination? 0 plus 0. We are not doing plus, we are adding it. Okay, 0 add 0. So 0 add 0. When we add 0 and 0, okay, so please look at here. Look at this point. When we add 0 plus 0, what is the result? Can you tell me? 0. Okay, 0 plus 1. When we add 0 and 1, what is the result? 1. 1 and 0, what is the result? 1. 1 plus 1, what is 1 plus 1? Yes, 2. Okay, what we are going to do now, please look at here. Now we are going to do this thing. So if we convert this into binary, if we convert this 0 into binary, this result will be 0 and 0. 0 1, the result will be 0 1. Then it will also be 0 1, and 2 will be 1 0. Okay, so can you see here now? Please look at here. Now, if you deduce this function, so what is this thingy? Okay, 0 1 1 0. This is F1 or F2? Can you tell me? This is F1 or F2? Help me. I'm not.
F1.
Yeah. So can you see here? This green thing is this your F1? And this red thingy, what is this red thingy? Help me.
F2.
F2. Okay, now can you see here? This is just like this is a 2-bit adder. So this is actually, it is a 2-bit adder. Why it is a 2-bit adder? It is adding 2 bit. So this is a 2-bit adder. So this is the block diagram of a 2-bit adder, and it means that now what I'm going to do is I'm writing it. This is it is a 2-bit adder. It is a so it is a 2-bit adder. It is a 2-bit adder. It is a 2-bit adder, 2-bit adder, and adding two numbers, two 1-bit numbers, which is A and B, and the output is F1. So what is my F1? F1 is now my F1 is called now my sum, and then F2 is now my what? Help me.
C out.
See out, carry out. So this is actually carry out. Any question? Any question? So okay, so this is how we do it. So now what is the design method? So now can you see here in the design method? So different combination circuit, we have the gate level design method and the block level design method. We are now starting with the gate level design method. So now this is my half adder. So this is my half. We call this as a half adder. Please remember, we call this as half adder. What is this thingy? Half adder is a 2-bit adder. It is actually a half adder. It's not a 2-bit adder. So it's a 1-bit adder. We call this as a half adder. Half adder. So it is now my half adder. It is not a 2. It's called as a half adder. This is not a 2-bit adder. Sorry, it is a half adder. We call this as half adder. Half adder. Any question? Any question? So what we are going to do now? So please look at it. It's a half adder. It is, we are okay. In this in the previous example, what was the input? The input was A and B, and the output was F1 and F2. But we call this as X and Y. So we are adding two bits. The first bit is X, and the second bit is Y, and C is your carry out, and S is your sum. Okay. Now can you see here? Now please look at here. Now if you look at here, this is the block diagram of a 1-bit adder. So can you see here? What I'm going to do? I'm going to here. What is 0 plus 0? Yes, can you tell me? Help me.
0,
0 plus 1,
1,
1. Okay. 0, 1 plus 0, 1. And 1 plus
1,
1, 1 plus 1,
2,
2. Okay. Can you see here? Now, please look at here. Now, what we do? So, this is actually, this is the code. This is the code for what? This is the code for 0. What is the code? These two codes. Help me.
1,
These two are the code for what?
1,
1. And if you look at the last one, it is a code for what? Help me.
2,
2.
2. Clear? So now can you see here? Now this first thing, please remember, this first thing is my carry out, and this thing is my sum. Okay, now if you look at here, now this is very important. So if you look at here, so carry is 1. So this is my 1. So this is my 1 here. So carry will be 1. So carry will be 1 when x is 1 and y is 1. So what is C? C is now equal to x dot y. Can I write? Any question? And now what is my sum? My sum will be 1. So now can you see here? Now my sum will be 1 when x is 0. So sum will be 1. So I can say sum will be 1 when x is equal to 0. Clear? Sum will be 1 when x is equal to 0 and y is equal to 1. Or sum will be 1 when x is equal to what?
1,
1.
1,
and y is equal to 0.
0. So if we derive the expression for this thingy, so what will be the expression? So can you see here the expression will be what? Help me. X bar y plus what?
Y bar x.
Okay, or x bar y plus x y bar or y bar x. It's also, and if you look at here, which gate is this? Which gate is this?
XR.
XOR.
XR. So this is a now exclusive OR gate. So now this is an exclusive OR gate. So can you see here? Now we got the expression for S, which is an exclusive OR gate. So this is an exclusive OR gate. So this is X exclusive OR Y. This is exclusive OR Y. So this is this gate. Any question? And now this is an AND gate. So this AND gate is now. Can you see here? This is now my AND gate. This is my AND gate, and this AND gate is the expression of X dot Y. Any question? Should we proceed? Okay,
Yes.
please remember, this is very important. This is very important. Okay, now if you look at the block diagram of the half adder, so there are different implementations of the half adder. There are different implementation of the half adder, and now we see. So now can you see here? This is the AND OR logic. This is now the AND OR logic. In the AND OR logic, the first level. So basically, we are also derived the expression for S. Please remember in the first in the please thing. So this implementation, can you see here? X bar Y and X Y bar. This is a stop implementation or pause. This one. This is SOP implementation. So can you see here? So now please look at here. Now in the first case, this is a SOP implementation. So this is actually x y bar plus x bar y. This is the SOP implementation. Okay. Now in this SOP implementation, can you see in this SOP implementation? So the first level. So the first level in this in the first level in this SOP implementation. What level is this? Can you see here? Anyone? This is called as AND logic. And the second level. Yes, anyone can help me.
OR
Second level.
logic.
Or. So this is called as AND OR logic. So this is AND OR logic. Any question? Okay, now if you look at the pause implementation, so please in the pause implementation, in the SOP implementation, we are interested in logical one. In the SOP implementation, we are interested in logical one. So can you see here the sum? This is this one and this one. So if we go for this one is actually x bar y, and the second one, it is actually x y bar. So this is actually
Y bar.
yeah, and this is okay. Now in the pause implementation, so can you see here in the pause implementation? So what we are going to do? So what we are going in the pause implementation. So what you are going to do? So now I'm going for the pause implementation. Now this is my pause implementation. Okay. Now this is my pause implementation. In pause implementation, are we interested in logical one or logical zero? Please help me. Yes.
0.
Logical 0.
So this we are interested in logical zero. So can you see here? This is actually for the pause implementation. This is what? This is actually this thing is actually x plus what? X plus y, and now I'm using the green color. I'm now using a green color. So can you see here the green color? So I'm now using the green color for this. And what is the value for this? Anyone help me?
X bar plus Y bar.
Yes, x bar plus y bar. So x bar plus y bar. And can you see here? This is x plus y and x bar plus y bar. So this the same thing. So this is the first thing. Please look at here. This blue thingy. So now I know I'm now looking the first color. So now this is my first color. This purple thing. So this is actually the first thingy, which is this thingy, and the second thingy is this thingy, this one. Any question? So this is the POS implementation or SOP implementation? This one.
Pause.
This one is the POS implementation. So this thingy is the POS implementation. So this is the POS implementation. Okay, and in the POS implementation, the first level. Can you see here the first level? Which logic here there? First level. First level is OR logic, and the second level is what?
And logic.
And logic. And can you see here now we also do this thing. So this called is the logic sharing approach. We call this as the this is inverted POS. And now can you see here the last one? We already derived the expression for S. What was the expression for X? S exclusive or Y. We already derived it here. And what is C is equal to X Y. So can this approach is called as the mixed gate approach. In this mixed gate approach, we have the first or exclusive OR gate, and the second gate is now an AND gate. So this approach is called as the mixed gate approach. So there can be a lot of implementation. There can be a lot of implementation for an adder. So now can you see here what I'm going to do? So now this is now tricky. This is now tricky. Can you see here? So let's assume if this there can be a lot of implementation. So now can you see here? If you look at this adder, now let's assume this adder. This is the POS implementation or SOP implementation? Can you tell me? Yes.
SOP
SOP.
implementation.
SOP implementation. So now this is a SOP implementation. If I ask you in the exam, oh, implement the NAND logic, the NAND logic. So how can you do the NAND logic? Okay, if you do the NAND implementation, see we put a bubble here, yes, then we put a bubble here, and to cancel out its effect, we put a bubble here and we put a bubble here. Okay, now when we do this bubble here, so we can push this bubble from the input to the output side. So can you see here, how can we convert this? So now it will make it like this. So this will be the first NAND gate. So this is my first NAND gate, and now we will have a second NAND gate. So can you see here the first NAND gate and the second NAND gate, and then we do the green thingy. So the green thingy, then we have the third NAND gate. So basically this is actually, can you see here the green thingy? This is my which gate? This is my negative OR gate, and negative OR gate is equivalent to a NAND gate. So this is now this is now we have, can you see here, this is X, now this is Y bar, and then we have X bar and X bar and Y, and now the output is now sub. Which implementation is this? Help me.
NAND.
NAND implementation. So we can have a lot of implementation. We can have a lot of implementation. So following the same argument. So can you see here now? Can you see here Control C, and not what I'm going to do. So now I'm going to Control A and then done. So please look at here. Now we derive this expression. This is okay. This is the SOP implementation or POS implementation. Can you all help me? SOP or POS?
POS.
So now this is my POS implementation. So can you see this is POS implementation? And this POS implementation, the first level is OR gate, and the second level is AND gate. And if you want to convert this into a NOR implementation, NOR implementation. If we want to convert this into NOR implementation, what should we do? So we put a bubble here, then we put a bubble here, we put a bubble here, and then we put a bubble here. So then this will be the NOR implementation. The first NOR gate, and then we have the second NOR gate, and now this we push the bubble on the output side. So can we see here this thingy? And then we can have the bubble on the output side, which is the red color, and this will be a NOR. So this is a NOR implementation. So this is a NOR implementation. And can you see here for the second one? We also want to convert this into NOR implementation. So if you want to convert this into NOR implementation, what will be the NOR implementation of this gate? This is an AND gate. So the NOR implementation will be something like this. So this will be the NOR. Remember, we do this. This is actually the first NOR gate inverter, the second inverter, and then the third. Any question? So this is actually what? X and Y. What will be our output? Help me.
X and Y.
No, the input is X and Y and the output is C. This is actually please remember, this is a NAND AND gate, and this is actually the NOR implementation of the AND gate. Remember? Any question?
No, sir.
Okay. It's already, you have already covered all of these things. Okay. Now, what we are going to do, now we want to design. Okay. So please remember, in the previous case, we were adding, adding to 1-bit number. Okay. Okay. Now what we are going to do, now we want to design a full adder. And how full adder will work on. So basically, for full adder, we need some explanation for the full adder. So I'm going to explain it. Okay, control. Okay, assume that we want to add two numbers. Assume we want to add two numbers. A, which color is A? Help me. Which color is A? Red.
Red.
Right. Assume we want to add two n-bit numbers. So we want to add two n-bit number. We call this as a n minus one, a n minus two, and blah 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 until a1 and a0. And we want to add another number b. Which color? No one is replying.
Green.
Green color, and then b1 and b0. And then we want to add these two number. I call this, and then I'm now using the blue color s. This is my sum. So how can I write it here? S0, then s1, and blah blah blah. Then what? S n minus 2, and then s what?
N minus 1.
S I minus 1. Okay. When we want to add these number, okay. So can you see here? This is okay. Now let's assume that n is now. Let's assume n is now 3. So let's assume n is now 4. Okay, when we are adding these number, okay, so what we do, so please look at here, when we are adding this number a0 and b0, so this the sum is c0, it will generate a carry, it will generate a carry to the next stage. We call this carry as what? Help me. C1.
C1.
Okay, and then when you are adding these two, so we generate a carry what? Then generate a carry what? C2, and so forth.
C2.
So C1. So what will be the carry here? Cn minus 2. And what will be the carry here? Help me.
Cn minus 1.
Cn minus 1. And the final carry will be what?
Cn.
Okay, now take an example. Now we take an example. Let's assume n is equal to 4. Okay, so since n is equal to 4, so we are adding to a. So what is my a here now? N is equal to 4. It is actually what? A3, A2, A1, and A0. And now what is my b in here now? So b is what? Help me.
B3, B2, B1, 0.
B1 and B0. When we are adding these two numbers, so we get S0. We get S0. Okay, we add A0 and B0. Okay, and then it will generate a carry. This carry will be what? C1.
C1.
Okay, and then when we add these two C1, A1, and B1, so we got S1. Okay, and then it will generate me a carry. What is the name of that carry? Help me.
C2.
C2, and then we got another sum which is S2, and then it will generate me a carry which is actually C3, and then we got this what? S3, and then we get this carry which is called as C4, and this C4 is nothing but C out. We call this as C out. Any question? Okay, now
No, sir.
please remember. Now we want to design a one-bit adder. Please remember. So actually, can you see here? Now please remember here. Now we have some index. I call. Please remember. This is very important. This is very important. I call an index I. I call an index I. What is the index here for the first stage? 0. What is the index here? Help me.
1.
1. What is the index here?
2.
2. And what is the index here?
3.
3. Okay, so now what we are going to do, so now we are going to have one bit. So now let's assume what is the range of I. So far, let's do. What is now the range of I? Can you tell me what is now the range of I? In
0
general.
to n minus 1.
So the range of I will be from 0 to n minus 1. And since in this example, n is equal to 4, so the range of I will be 0 to small equal to I, small or equal to 4 minus 1. So this will be 0 to 3. So this the range of I is equal to 3. So now what we are going to do now? What we are going to do? So what we are going to do now? We want to design a one-bit adder. So now in this for this thingy. So for this thingy. So basically in this thingy. So now what is my here? What is my I here? I is now 1. Okay, so can we design an adder? So now we have, so please remember. So now we want to design a one-bit adder. What are the inputs to a one-bit adder? A full adder. It's a full adder. What's the first input? Can you tell me what's my first input and what's my second input in terms of I? What is the input? Anyone may tell.
AI, BI, and CI.
AI. Very good. The second input.
BI,
BI. And the third input.
CI,
CI. And then we have the outputs. Okay, so the AI is input, which is actually the red color. So AI is the first input, the red color. This is the AI, and then we have the BI, which is the green color, and then we have the CI, which is actually this. And now we have some output. What is that output? And can you tell me? Yes,
S I and C I plus 1.
yes. And the output is SI, and the second output is actually CI plus one. It will go to the next stage, CI plus one. Any question? Any question? Clear? Okay. What we are going to do now? So now what we are going to do? So now what I'm going to do? I'm going to rub everything off. Okay. Now this is the block diagram. So now this is the block diagram of a one-bit adder. So now this is the block diagram of a one-bit adder. And please remember, we have the first input, which is actually AI. Then we have the second input, which was the green color, which is BI. And then we have the third input, which is actually CI. And the output is now, can you see here, there are two outputs. So this is actually SI. And then we have the other output, which is actually CI. So CI plus 1. Okay. So can you see here for this in this example, how many inputs are there?
3.
Three inputs. So how many entries in the truth table?
8.
8. AI, and then we have BI. And please look at the color coding. I'm using a lot of color coding. So now we have this BI, the second input, and then we have the CI. So you can see here, this is my CI. And then we have the sum. Okay, then we have CI plus 1. So this is actually CI plus 1. And then the second output is what? What is my second output?
SI.
SI. Now can you see here? Now this is a 0, 0, 0, 0, and then 1, 1, 1, 1. Now if you look at the CI, this is actually 0, 1, 0, 1, 0, 1, and 0, 1. And now if you go to the BI, which is the because this is actually 0, 0, this is 0, sorry, 0 control Z. Any question? Okay, now can you see here? Now please look at here. Now please look at here. If we add 0 plus 0 plus 0, what is the result?
0.
0. 0 plus 0 plus 0, the result is 0. 0 plus 0 plus 1, 1. 0 plus 1 plus 0, 1. 1 plus 1, 2. 1. 1 plus 0 plus 0 is 1. 1 plus 0 plus 1 is 2. 1 plus 1 plus 0 is 2. And 1 plus 1 is actually 3. So can you see here? Please now look at here. So now this output is 0. Please look at here. Here the code will be 0, 0. Okay. Now I'm now using this black color. So this is actually black color. This is my black color. So the output is 0, 1 here, and 0, 1 here, and 0, 1 here. Now I'm using the green color. So the green color is actually 2 here. 2 is actually 1, 0, and these 2 is what? 1, 0, and 1, 0. And what about the other color? So now I'm using the purple color, and this one 3 the purple color. Any question? Any question? Should we proceed? Okay. Now we have, if you look at the truth table of this full adder, so this is called as a full adder. If you look at the truth table of full adder, so now we can find the expression for Ci plus 1. And how can we write Ci plus 1? So Ci plus 1, Ci plus 1 is what? Sigma m. Sigma m of what? Can anyone tell me? Is 0, 1, 2, 3, 4, 3,
3,
4,
5, 6, 7.
7. So this sigma m is actually 3. Yes? 3,
5, 6, 7.
7. And what is now SI my SI? Help me.
2, 3, 5, 7.
Yes, it is actually 0. No, SI
No,
1.
1, 2,
1,
1, 2, 4,
2,
7.
1, 2, and then what? 1, 2,
4,
3,
7.
4. So we find the expression for Ci plus 1. Okay, what should be my next expression? If you convert this into sigma m form, yes, then okay. Now what is my Ci plus 1? So what is my Ci plus 1? What is my Ci plus 1 in pi m plus form? Help me. Pi m.
1,
0, 1,
0,
2.
1,
1, 2, 4. And what is Si in pi m form? Help me.
0, 3, 5, 6.
Five,
Oh,
six. Okay, please remember, if you want to find the SOP expression, so we for this will be used for SOP expression, and this will be used for what? Help me.
pause.
Past expression. Please remember, so okay, we can say, oh, we design a past expression, soft expression. So and you can do it in the NAND implementation. So first, if you want to have the NAND implementation, so first you will derive the soft expression, and from soft expression you can do the NAND implementation. And if you want to ask the NOR implementation, so first you will convert it into POS, and then you convert it into NOR implementation. Any question? So what we are going to do? So now, can you see here? So now this is actually my the whole thingy. We want to design this one bit adder. This is the thing here, the same thing that I explained it. Okay, so this is actually okay. Please remember, in the example that we did it. So basically now in this example, so they are using x, y, and z. And what I used in my example, what was this thingy? Help me. AI
A1,
and AI, not A1. And then it was what?
BI,
BI, and Z is what?
CI,
Okay, and then can you see here now what is this C? This is actually CI
I
plus
plus
what?
1,
Plus one, and this is what? Help me.
SI.
SI. Okay, can you see here now we want to find the expression, SOP expression. So in the SOP expression, so can you see here in the SOP expression? And now please look at for the SOP expression. So can you remember the SOP expression? So for the SOP expression, we can do that. Okay, so we can do the SOP expression. This is 0, 1, 3, 2, 4, 5, 7, 6. And can you see here? What is now we want to find for C. C is what? 1 is here, 4. So how many ones are there? 4. 0, 1, 2, 3. 0, 1, 2, 3. 3. So there is a 1 here. This is 3. Clear? And now you can do it. So you find the expression for C and X. Okay, so in the next step, should we draw the K-map? So can you see this is not my K-map? We draw the K-map. How many ones are there? So basically, C is now, and now we already found that expression. So can you see we found an expression from here? Remember. We found an expression for there. Okay. Now, what is my CI here? CI. What is now? I'm just going to find this. CI is what? Help me.
CI or CI plus 1?
CI plus one. Yes.
It's
Sigma
X,
M
oh, 3, 5, 6, 7.
3, 5, 6, and 7. So 3, 5, 6, 7. So can you see here? So if 3, 5, 6, 7. So now can we? So this will be 1. 5 will be 1. 6 will be 1, and 7 will be 1. So can you see here? This is the same pattern. Got it? The same pattern. So similarly, you can find it for S. So we found the expression, the K map. We draw the K map for CI. So this is the map for CI. So now these are all ones. So these are the okay. Can we group them? Yes. This is the first group. Which color? Which color?
Blue.
Blue color. See, so the expression is what? X, Y. So X is 1 and then Y is 1. Another expression, which color? Red color. So it's red color, we find expression for X, Y, and then it's for Y, Z. So this is actually Y is 1 and Z is 1. And similarly, we found expression for S. How many ones are there? There are 4 ones. 1, 2, 3, and 4. We fill all the ones. And then can you see here? This expression is what? X bar, Y bar, Z. So the red color. This is the red color. Please remember this is the expression for red. And this is the black. What is black? X bar, Y, and Z. Clear? The black color. X bar, Y, and Z bar. And the green color. What is the green color? X, Y, and Z. So this is okay. Can you see here? These two implementation. Now, if you look at these two implementation, this implementation. SOP or POS? SOP. And this implementation. Help me.
SOP.
SOP. Both are SOP input. In the exam, I may ask for the POS implementation. If you have the POS implementation, then you will solve for. Any question? Should we proceed?
Yes.
Okay. Only one guy is replying. Many of them. Okay, so we have only 18 participants. Oh man. Oh, man. Okay, no one is replying other than them. So what about Mira? What about Mubin? What about Rashid? What about Reem? What about Shama? What about Rex? Sidra? Thomas? Thomas is replying, yeah. Abir? Abdullah? So please, I need your participation. Participation is very important. I know that it's a little tricky. Okay. Okay. So now we found expression for C, which is actually xy plus yz and z. So can you see here? And we do some Boolean algebra. We do a lot of Boolean algebra manipulation. Why I'm doing the Boolean algebra mathematics, I will explain this. So can you see here? So now what is the common term here? So in this case, the common term is z. So z is now the common term. So it is x plus y. Okay, how can we write this x? This right, we can write this x as xy plus xy bar. We are expanding. We are expanding. And we further minimize thing. So what is the common term here? So the xy is common term. So this is a plus a. What is a plus a is a. So we are writing it only once. And then what is this x y bar plus x bar y? It is exclusive or y. And then we further minimize this expression. In the final, we got this xy plus x exclusive or y. And then can you see here? Now, if we find the expression for x, what is x bar y bar z bar? What is the common term in the red one? What is the common term in the red one?
X bar, just X
X
bar.
bar z is the common term. And what is the common term in the blue one here?
X bar Z is in common, just X bar, yeah.
Yeah. So yes, x bar is common. Here you are right. It's x bar is common here. And in the second one, what is the common term? X.
X,
X
So yes, we take the common term. And what is y bar z plus yz bar? Which gate is this?
XOR gate.
XOR,
XR. And which gate is this? This one. This one.
X NOR,
X NOR. So can you see here? So we can get it right. So this is actually y bar z, y is exclusive or z, and this one is y is exclusive or z whole bar because it is exclusive NOR gate. And we further minimize it. So this is actually the exclusive OR implementation. So can you see here? Now, the circuit for the above formula now is what? Okay, now which implementation is this? Which implementation is this? Help me. Because there are different implementations. We
a
have the soft
mixed,
implementation. This is the mixed gate approach. And in this mixed gate approach, how many exclusive OR gates are there? Yes, help me.
2,
Two exclusive OR gates. How many AND gates are there?
2,
2,
Two AND gates. And how many OR gates?
1.
1,
One. Now please think of this thingy. So please remember, think of this thing. If you look at these two blocks, what is these two blocks? Can you see? What is these two blocks? This block.
the half adder or the full adder
And
for 1 bit.
is a half adder. So you can design a full adder. You can design a full adder using the SOP implementation. You can design the full adder using POS implementation. You can design the full adder using NAND logic. You can design the full adder using NOR logic. You can design the full adder using mixed gate approach, and we have designed it now. But you can also design a full adder using half adders. So can you see here? So now this is the common term. Okay. And now can you see here? This is now my half adder. So full adder can also be designed using in half adder. So for full adder, how many half adders are required? How many half adders are required for the implementation of the full adder? Yes,
2,
2,
two. And how many OR gates?
1.
1,
One OR gates. So we can also design the full adder. So now there are different implementations. So can you see here? This is actually, can you see here? This one. This implementation. Can you see this implementation? Which implementation is this? Yes, this one.
and or
And or the SOP implementation. Clear? This is also and or which implementation?
SOP,
SOP implementation. And how do we get this SOP implementation? By drawing the K-map. How many K-map do we need? So for the, please remember, for the blue color, this is my blue color. So this blue color, so we have the blue color represent the K-map for C, and the red color represent the K-map for S. And then we derive this truth table. So this is the AND OR logic. So this can you see? This is C, and now this is my S. And now, which implementation is this? Yes, this which implementation is this? Help me
mixed,
get about. Which implementation is this?
and or SOP.
And or SOP. So can you see here? Now we have, okay, now what implementation is this? Can anyone tell me which implementation this? Can anyone explain me this thing?
NAND,
No, no.
uh,
Is it an AND gate? Can anyone tell me? This is very tricky. This is very tricky.
is this also and or?
This is also and but I will now going to explain it. Okay, this is another implementation. Okay, so what I'm going to do, so I'm going to remove this thingy. It's visible to you? Everything is visible to you? Yes or no?
Yes, Professor.
Yes. Okay, please look at here. Now I'm using the red color. The red color. What is carry I plus 1? Please give me in sigma m form. Help me. Yes.
3, 5, 6, 7.
3, 5, 6, and 7. So this is actually 3, 5, 6, and 7. Am I right? Yes. Can I write this thing? M3 plus what?
M5 plus M6 plus M7.
Any question? Okay. Now what I'm using a green color for SI. What is SI now? Help me.
1, 2, 4, 7.
1, 2, 4, and 7. M1, M2, M4, and M7. Am I right? Okay. Now can you see here? So M1, it is M1, so can we write M1 plus M2 plus M4 plus M7? Any question? Okay. Now if you look at this M1, now just look at M1. So now look at M1. What is M1? 0, 0, 1. What is M2? 0, 1, 0. What is M7? Yes, what is M7? Help
1,
me.
1, 1.
1, 1, 1. What is M6? 1, 1, 0. What is M5? 1, 0, 1. What is M3? 0, 1, 1. So can you see here now for this thingy? Oh man, this is just okay. I made a wrong thing. So now can Control C. Clear? Okay. Now please look at here. So 0, 1, 1. So can you see here? This is actually what is this gate? 0, 0, 1. Please look at here. This is 0, 0, 1. What is this thingy? Help me.
M1.
M1. 0 because this is M1. This is actually because this is bubble. It is 0, 0, 1. What is this thingy? 0,
1, 0, 1, 0.
which
M2.
is what? M2. And 0, 1, 1.
M3.
3, 1, 0, M4,
M4.
M5,
M5. M6.
M6,
M7.
and then what?
M7.
Okay, now I'm using the red color. So red color Ci plus 1. So this Ci plus 1 is M3. What is M3? So M3 is going here. Any question? This is M3, then M5. M5 is here. M5 is going here. Any question? And then what? M6 and M7. So M6 is going here. And then M7 is going here. Any question? Now for the second one,
No.
SI. I'm now using the green color. The green color. What is going here? M3. Where is M3? No, sorry, M1. M1 is now going here. It is M1. And then what? M2.
M2.
M2 is coming here. And then what?
M4.
M4 is coming here. M4 is coming here. And then what? M7. M7 is shared between these. Any question? Clear? So this is actually Ci plus 1. And this is now Si, which is there. Any question? This is the expression.
So,
Got it?
Professor, this is the unminimized implementation?
This is the unminimized implementation. Yes, this is the unminimized implementation. And this is also another implementation. This is how do we call it? Any question? Any question?
But it's and or logic, right?
Yes, this is and or logic. Yes, this is and or logic. This is minimize and or logic, but you are using all the min-term based approach. Any question?
Professor, can you explain what's the difference between a full adder and a half adder?
What's the what?
What's the difference between a full adder and a half adder?
Yes, in a half adder there is no carry in, and in a full adder there is a carry in. Okay,
Okay, so here only Z isn't there in the truth table for a half adder.
half adder, so what is in the half adder? See, in the half adder we don't have any carry in. And please remember, whenever we are adding to, when we are adding to n bit number, for the last stage, for a0 we do not need a carry in. So for the a0 we can use half adder, and since it generates, it may generate or it may not generate a carry. So for other stages, a1, a2, a3, and blah 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 until an minus 1, we need full adder. Any question?
No, sir. Thank you.
I hope I answer your question. Yes.
Yes, sir.
Good. So now what's there? So now we have to see, we have where it is. Okay. Now how can we design a combination circuit? So if we want to design a combination circuit, we specify the inputs and then we specify the outputs. So let's assume if we want to have a half adder, what are the inputs? So the inputs are x and y. What is my output? It is actually si and ci plus 1. This is my half adder, not full adder. If we want to have the specification for the full adder, what are the inputs? AI, BI, and CI. And what are the outputs? SI and CI plus 1. So this is the specification. And what's the specification does? Then we formulate the problem. We formulate the problem into truth table or the logic expression. We formulate a truth table. We derive the truth table. So in the second thing, we derive the truth table of the half adder, and then we derive the truth table of the full adder. Then we did the logic minimization. So we do the logic minimization using the K-map method or the Boolean algebra method. Okay, so for the K-map method, we can have the SOP implementation or we can have the POS implementation. And then we do the technology mapping. We can use the SOP implementation, we can do the POS implementation, we can do the NAND implementation, we can do the NOR implementation, we can do the mixed gate approach implementation. So there are a lot of implementations. So these are all the steps that how can we design a combinational circuit. And now I will explain this with an example. Now we want to design a code converter. What's a code converter? So in the code converter, we have some input code and then we have an output code. And I'll explain this with an example. So we want to design a BCD to XS3 code converter. So we want to design a BCD to XS3 code converter. Okay. So what we are going to do and how we will design it, I will explain it. So I'm going to control A. So we want to design a BCD to XS3 code converter. Okay. So let's assume we have this BCD. So this ABCD is my BCD. So this is my BCD, and the output is actually XS3. So the XS3, which is actually now XS3, W, X, Y, and Z. So this is my which code? Which code? XS3, and the input is what? Which code? Help me. Okay. Now, if you look at here, the BCD code. So now we draw for A, B, C, D. So this is actually A, B, C, and D. And what is my output? W, X, Y, and Z. Okay, how many combinations are for A, B, C, and D? 16 combinations. 0, 0, 0, 0, then what? 0, 0, 0, 1, then 0, 0, 1, 0, and blah, blah, blah. And then 0, triple 1, then 1, triple 0, and then 1, double 0, 1. Okay. And then 1, 0, 1, 0, 1, 0, 1, 1, and blah, 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 until 1, 1, 1, 1. Okay, please remember, this is the code for what? Help me, this is the code for what? 0. This is the code for what? Help me. 1,
1, 2,
2, and this one
7, 8, 9,
8, and then what? 9.
9,
Okay, now if you look at here, the green thingy. So what is the code for this? Help me.
10,
10, 11,
11,
and
15,
how many combinations are there total for BCD? Total
16,
16 combinations. Okay, out of these 16 combinations, the black one are the valid codes or invalid code?
valid,
Valid code. And the green one?
invalid.
Okay, now please remember. So what is my output now? Please remember what is XS3 code? XS3 code. So now we are going for XS3 code. XS3 code is nothing. XS3 code is nothing but plus 3 of BCD. So if the input is 0, what will be my output? XS3 in XS3 code? Yes.
3.
3,
3. Okay. So now can you see if the input is 0, my XS3 code, now you use it, it will be 3. If the input is 1, what will be my output? Help me.
4.
4. And if the input is 0, what is my output? 5. And if the input is 7, what is my output? 10. Input is 8, what is my output?
11.
11 and 12. So can you see here now? Please look at here. What is now? So these are the for XS3 code. What are the valid codes for XS3? Help me from 3 to what?
12.
So XS3 valid codes are from 3 to 12, and BCD valid code are from what? 0 to what?
9.
9. Okay. Now if we convert this 3 into binary, what will be the code? Can anyone tell me? 0011. What will be the code for 4?
0100.
And what is the code for 5?
010.
0101.
Code for 10. And what is code for 11? What is the code for 12?
1100.
Any question? Any question?
No, sir.
Okay. Now please look at here. Now what I'm going to do now please, because these are all invalid code. So what will be all outputs here? Here W X Y Z or from 10 to 15. Yes. Can you tell me?
Sir, could you repeat?
Yes. What will be the output for W X Y and Z for 10?
It won't matter, yeah, because it's
Yeah, it don't
invalid.
matter. Where should you put?
DN.
Don't care. Why don't care? Because we want to minimize our logic. Okay. How many don't cares will be in the truth table? How many don't care will be in the truth table for each truth table? Help me.
6.
6 don't care. So there will be 6 don't care. So can you see here now? Can you see here now? If you look at here, so we find the expression for XS3. This is actually okay. Now, how many? Okay. Now, if you look at here, how many inputs are there? How many inputs are there in this example? We draw the truth table. So can you
4.
see here? So these are the valid codes. These are the valid codes, and these are the invalid codes. Okay, for the invalid codes. So this is 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And the valid value of XS3 are okay. Now please look at the W. Which color? W. Yes, which color?
Red.
Right. X.
Blue.
Blue. And Y black, and Z is green. So can you see here now? W is a function of A, B, and C, D. X is a function of A, B, C, and D, and Y is a function of A, B, C, D, and Z is a function of A, B, C, D. Okay, now what we are going to do? Now let's say we want to find W. What is now W? Can you tell me W? How can we find W? Help me. It is actually sigma M what? Help me.
6, 7, 8, 9. No, 5, 6, 7, 8, 9.
5, 6, 7, and what?
8, 9.
8, 9. Plus, there should be also something more. Help me.
Sigma D of 10, 11, 12, 13, 14, 15.
11, 12, 13, 14, and what? 15.
15.
What will be the expression for X? What will be the expression for X? Can you tell me?
1, 2, 3,
Sigma M
4.
1, 2, 3, 4, 9.
M 1, 2, 3, 4, 9 plus sigma D
10 to
10,
15.
11, 12, 13, 14, and 15. Similarly, we can find an expression for Y, we can find an expression for Z. Please remember, in the exam, I may ask, find the SOP expression for W. So we will be interested in sigma M. Find the pos expression for W. So we'll be interested in logical 0. Interested in the pi expression. And then we can combine don't care with all of these things. So can you see here? Now, please look at here. So now, can you see here? Now, okay, now in the K-map, if you look at in the K-map, we draw the K-map for W. Okay, how many ones are there? How many ones are there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. How many don't cares are there? 1, 2, 3, 4, 5, 6. 1,
6.
2, 3, 4, 5, 6. Any question?
No.
Got it? So what we do?
Yes.
What I'm going to, can you see here? Now what I'm going to do is I can what I'm going to do, so I can control C and then I can make it control V. Okay. Okay, now just what we are going to do, we are only solving for W. So please remember, now if you draw the K-map, so please remember this is very important. I need your attention here. And please, this is very important question in exam. So basically what I'm going to do is I'm now using the red color. Okay. Now please remember, we already find the expression for W. What was W? Help me. W, what was W? Help me. Yes. W was what?
Sigma
M what?
M 5,
6,
6, 7, 8, 9 plus
7.
sigma D 10 to 15.
And what?
9.
9 plus, and then we do the sigma D. Okay, so sigma D 10, 11, 12, 13, and then what? 14, and then what?
14, 15.
52. And if you draw the K map, remember the K map, so we do the K map something like this. Remember what was the K map? Help me. 0, 1, 3, 2, 4, 5, what? 7, 6, 10, 11, 9, 8, then what? Help me.
12, 13, 15, 14.
13, 14, and 15.
15,
Remember?
14.
12 and 15, 14. Yes, this is 15 and then we have 14. Yes? Okay. Now can you see here? Now if you do that thingy, so now how many x are there? So these are x. So these are x. So can you see the x thingy? So now in the x thingy, I'm now using this color. So I'm now using this color of this blue color. So x is actually, these are x. Can you see here? 10, 11, 12. So this is 10, 11, 12, 13, 14, and 15. These are x. So can you see this is my x? Any question? Any question?
No.
And what now? What about my base thingy? So now this is 5, 6, 7, 8, 5, 6, 7. So this is 5, 6, 7. So this is 5, 6, 7, 5, 6, 7, and then 5, 6, 7. So this is 5, 6, 7. So this is 5, 6, 7, and then 8, 9. This is 8, 9. So these are 8, 9. Any question?
No, sir.
Similarly, we can draw the KMF for Y. Similarly, we can draw the KMF for Z. Similarly, we can draw the KMF for X. Any question? Got it? Now, what we do? Now, we do this thingy. Okay, so this is what we do. So we draw the KMF for. Okay, and then we have this KMF. Okay, we draw the KMF for W. We draw the KMF for what? X.
X,
We draw the KMF
Y,
for
Z.
Y, and KMF for Z. And then we see here, so these are the KMFs. Okay, now we do the logic minimization. Okay, what is W? It is actually A. Please look at here. A which color?
Green.
Green color. So basically, it's a large group for A. So can you see here? So now we do, it's a green color. So this is actually whole thingy, the green thingy, this green. And this green belongs to. Any question? Then we have BC, this BC. So now this BC, so now we are using this color. So this BC, BC is the group of this group. And now we have the blue color. So now we have the blue color. This is BD, and this BD is this thing. Any question? Clear? So what do we do? We find the expression for W, then we find the expression for X. So this is find the expression for X. Then we find the expression for Y, and then we find the expression for Z. What is Z? And then for Z, this is very simple. We can make a large group. So we can make a very large group for Z. So this is actually this large group for Z. This is large group for Z. And if you go there, AB is changing, and then if you go from here to here, what is the value of C? C is changing. C is 1, 0, and then it is Z is equal to D bar. Any question? Any question? Should we proceed?
Yes, sir.
Okay, now what we are going to do? Now what we are going to do? So now we are going to do more tricks. Now we are going to do a lot of more tricks, and let's see what are these tricks. Let's see what are these tricks. Okay. So now please remember, using the K-map method, so we find the expression for W, X, Y, and Z, and you already know the K-map method. What is the common term here in this common term here? B is the common term, so we can write C plus D. C plus D is which color?
Right.
Red color. Okay. So then this is the expression for X. What is the common term? We take common term. So now in these two examples, what is now the common term here? The common term now is
C plus D.
And now can you see? Now this is the blue color. The blue color is now C bar D bar. Can we apply De Morgan's theorem and convert it into the form of C plus D? Yes. What should I write?
B bar plus C
No,
plus D.
I want to convert this expression into C plus D form. So can I write it actually C bar D bar is actually equal to C plus D whole bar. C bar D bar is equal to C plus D whole bar. So can I write it here? So now it is the common term here. Now the common term here is C plus D. And again, we again have C bar D bar. How can we write it? This C bar D bar, we can write it C plus D whole bar. And now it is expression for D, which is actually D bar. And can you see here? So C plus D is the common term. So C plus D is the common term is Y. C plus D is also the common term in X, and C plus D is also the common term in W. So now this approach is called. Please remember, this approach is called as which approach? Can you tell me which approach is this?
Uh, oh,
Please remember, this is called as the logic sharing approach. In the logic sharing approach, we identify what? Help me. We identify what in the logic sharing approach? Please help me.
Common terms.
We identify the common term. And in this particular example, what is now the common term in this particular example?
C plus D.
C plus C. So in this case, we have identified the common term, and then we find the expression for W. So we can see here, this is the we have the expression for W. Now we have the expression for X. Then we have the expression for Y. Then we have the expression for Z. Any question? Now, please remember, this is now which method? This method in the logic sharing. So please remember, KMap will not always give us with me the minimized expression. So what we do, if we get multiple expression, now in this particular example, there are four outputs. The first output is W, the second output is X, the third output is Y, and the fourth output is Z. And in all of these outputs, then we identify the common terms. And in this particular example, now we have identified the common term, which was C and C plus D. When we identify the common term, and then we draw the logic diagram of all the common terms, because this is called as the logic sharing approach, and we discussed already this in our previous lectures. Okay, now what we are going to do, now I'm now using another method, and that method is called as the mixed gate approach. So now what we are going to do, we are doing the mixed gate approach. So we find expression for W, then we find expression for X. So can we see, let's assume I'm saying, okay, let's assume this C plus D is P. So we P C plus D, and then you can say, okay, what is B bar P plus BP bar? Which gate is this? Which gate is this? Anyone help me?
XOR.
XOR. So we can write X is equal to B exclusive or P. So now X is equal to B exclusive or P. And now what is P now? P is actually C plus D. So I'm writing C plus D here. Then we find the, okay, now please look at here. This is actually CD plus C bar D bar. So can I write it here? CP bar and C bar P, where P is equal to D bar. Okay. And now if we convert this thingy, which gate is this? Yes, help me.
XOR.
XOR. So it is actually C exclusive or P. And what is P? P is actually D bar. And then we find the expression, because can you see here? Now this is D bar here. Why I'm using it? Because D bar is now the common term. So D bar is here, D bar is here, and now D bar is here. And if you derive this thing, so this which approach is this? Help me. Can anyone tell me which approach is this?
XOR mapping.
It is also XOR mapping. No, this is called as the mixed gate approach. This is called as the mixed gate approach plus the logic sharing. Why we are giving? Okay, now in this example, it is a mixed gate approach because we are using a mixed up gate. We are using exclusive OR gate. We are using OR gate. We are using AND gate. We are using inverter, and then we are also doing the logic sharing. Can you see which term is now the common term? Now please remember, this D bar is now the common term because D bar is used here, D bar is used here. And what is the other common term? What is now the other common
C
term?
plus D.
Plus D is another common term. So now in this approach, what we are doing, we are going to use a mix. We are going to we are using a mix of the logic sharing and the mixed gate approach with the common terms. Any question? Any question?
No question.
Clear? Okay. Now what we do? Once we derive all the expression, okay, please remember, I will now ask some question from the student. If some student will not be able to answer me this question, it means they were not attentive during the lectures. Okay, so I will be asking some questions. So okay, so now, and then we do the verification. So we do the verification. Okay, which approach is this? Yes. Now I'm going to.
Mixed logic.
No, 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 no. I will ask from Rashid. Yes, Rashid. Which approach is this? Rashid.
Yes.
Yes. Which approach is this?
Sure.
Reem. Which approach is this? Yes, Rex. Which approach is this? Now that's the problem. Huh?
Is it mixed?
No. So now very good. Please remember this is very important. And I will ask question. Please remember this may be the question in exam. So can you see here? Now, please look at here. Now what I'm going to do, and please I need your attention. This may be the question in exam. You're taking it not seriously, and it's not good. Okay. So what we are going to do? This approach is okay. I can make this. It is a which approach? Mixed gate approach with what? Logic sharing. What are the common terms? What are the common terms? Yes, can you tell me what are the common terms?
C plus D and D bar.
D bar is a common term. Please look at here. Why D bar is a common term? And I will explain it. So now you can see D bar. So D bar is now the common term. So now I can use the red. So D bar. So this is D bar. D bar is going here. Okay, and D bar is going here. So this is the common term. What is the other common term? The other common term is C plus D. So please look at here. So now please look at here. This is now C plus D because C plus D is going here and C plus D is also going here. Any question? These are the common terms. Okay? Okay. Now, here. Again, I'm asking this question. Which implementation is this? Help me. Yes.
Mixed gates and logic.
No, this one.
And or.
Stop. Which approach is this? Yes.
Mixed gate.
Mixed gate. What are the common terms here? What are the common terms here? This is the common term. X exclusive or y is the common term. Can you see here? And this is going here. Anyone? Yes? Because what is the common term here? S exclusive or y is now the common term because you can also find this from the expression. Any question? Any question? Okay, now please look at here. Here, this is also mixed gate approach. Look at just the expression. What are the common terms here? What are the common terms here? Here, help me.
X exclusive or Y.
And this is also a mixed gate approach. This is actually a mixed gate approach. Okay, now what I'm going to do, this is very tricky now. Please look at here. Which approach is this now? Which approach is this?
Mixed.
No. Now please look at here. No, not it's not a. Look at the yellow color. You look at the yellow color.
I'm still seeing the full address slide.
No, it is actually the block diagram approach. It means that you are available with some components. You are available with half header. You don't know what is inside that half header. You don't know. It is called as the block diagram approach. It's called as the implementation of the half header is not visible to you. How many gates are there in the half header? Do you see any gates in the half header in the yellow color? Yes.
No.
No, you do not see. This is called as the block diagram approach. In the block diagram approach, what you do, you are using an existing blocks to connect all of the components. This approach is called as which approach? Help me.
Block diagram.
Block diagram.
Block diagram approach. Any question?
No question.
Okay, please remember in the exam I'm telling you, if you're taking this non-seriously, you will face a lot of problems in the exam. And I'm telling you, this course is not easy. This course is not easy, and I'm also recording this lecture. So please, all the and please, you can, if you're not attentive at this point of time, please you can revise this lecture uh, again and again, because this is very tricky thingy. And I also posted some practice problems.